We're now going to look at how delta G changes with temperature. So how does delta G change with the temperature? Well, we have this equation that delta G equals delta H minus T delta S. And there's a trick we can do where we can make our Y value delta G and our X value is the temperature. And we can see how does delta G change with temperature. So if we rearrange this equation so that it looks like this, we have something that is in the slope-intercept form of an equation where y is equal to delta G, x is equal to the temperature, and the slope of our line is going to be equal to negative delta S. So furthermore, our y-intercept is going to be equal to the delta H. All of this is to help us understand what kind of reaction we're going to be looking at when we have various values for delta H and delta S. So if delta H happens to be a positive quantity and delta S happens to be a positive quantity, we'll get this result where it will be spontaneous at high temperature. I'm going to go ahead and show you all four of the results here. So what happens when delta H is positive? So positive, 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 negative, 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 and negative, positive. Those are our four possibilities for what happens. We're going to look at this on a graph, and I think this is a useful way of looking at it. Many people who look at this kind of graph, it helps them. And for other people, it's just memorize what's happening. I'm hoping you guys will get some benefit out of this. So again, our X value is going to be the temperature. So that is what the X value is here. And our Y value is going to be the Gibbs free energy. So our Gibbs free energy, which is the Y value in this equation. You'll notice that I don't have any negative values for temperature because our temperature is in Kelvin. We can't have negative quantities for Kelvin. So let's do each of these four. We're going to start with the blue one, which is positive, positive. If delta H is positive, then that means that our y-intercept is positive. So that line will intersect somewhere up here. And if delta S is positive, then that means that our slope is negative because our slope is equal to negative delta S. So negative of a positive will give us a negative number. Well, a negative slope is going to go down. So that blue line would look something like this. What this line tells us is over what range will this reaction be spontaneous? And we'll find that once we get to this temperature, the reaction will start to be spontaneous in the forward direction. Any temperature above that and the reaction will definitely be spontaneous in the forward direction because delta G is negative. If we're up here, so if we're below this temperature, we're going to have a delta G that's positive, and that will tell us that the reaction will not be spontaneous in the forward direction, and in fact will be spontaneous in the reverse direction. So this is going to be spontaneous at any temperature above this, and we're going to just call that spontaneous at high temperature. For our next possibility, plus minus, delta H is positive, so that means our y-intercept is going to be positive, so it'll be above the x-axis up here. And if delta S is negative, that means the slope, negative of a negative, is going to be positive. So this line is going to go up. So we get this. So you'll notice that that line is never going to be below the x-axis. And so we're never going to have any quantities of delta G that are negative, meaning that at no temperature will this reaction be spontaneous. So it is spontaneous at no temperatures. That's why I chose red for that one, because it's not going to be spontaneous at any temperature. For our next one, we've got negative, negative. Well, negative delta H means that our y-intercept is negative, so the y-intercept is going to be down here somewhere. And if delta S is negative, that means that our slope is positive. So negative of negative is positive, so it's going to go up. And so that will look like this. So for our black line here, it will be spontaneous at any temperature starting from absolute zero up to this point, And so at any temperature that's below that point, it should be spontaneous in the forward direction because delta G is less than zero. Once you get above that temperature, the reaction will not be spontaneous in the forward direction, and in fact will be spontaneous in the reverse direction. Our final example is this green one. If we have a negative value for delta H, that means our y-intercept is negative, so it's going to be down here. If delta S is positive, that means the slope is negative, so it's going to go down. Well, that's going to look like this. So this kind of reaction will be spontaneous at all directions, and so I chose green because I guess green means go, right? So I chose green to indicate what happens there. So let's do numbers 59 and 66. And 59 is a pretty straightforward and pretty easy. So it's pretty straightforward and pretty easy problem. All right, so classify each of the following reactions as one of the four possible types summarized. And so what we mean by that is it's spontaneous at high temperature, low temperature, at no temperature, or at all temperatures. And we just have to look at those four different values. Now, one thing before we do this, I recommend either memorizing this little table, or there's a slightly different version of it in the textbook, but memorize that table, or memorize how this graph works. You don't have to do both. I find it easier to think of it this way because that's how my brain works. But if you look at this and you're confused, then just memorize this table, and that will help. So we're going to go back and we're going to look. So here we've got this reaction. So nitrogen plus fluorine gives us NF3. Delta H is negative and delta S is negative. Well, negative, negative, we're going to go back to that table. Negative, negative is spontaneous at low temperatures. So we're just going to write, this is spontaneous at low temperatures. And that's it. Nitrogen plus chlorine gives us NCl3. And you'll see that delta H is positive, delta S is negative. So delta H is positive, delta S is negative. This doesn't look good. All right. We're going to go back here. Positive, negative, spontaneous at no temperature. Well, that's a good thing to know. If you're trying to do a reaction and you calculate delta S or delta H to be positive and delta S to be negative, well, you maybe should look at doing a different reaction. So this one is going to be spontaneous at no temperature. I suppose you could put non-spontaneous at all temperature, but I'm going to put spontaneous at no temperature. For this next one, we've got the N2F4 gives us 2NF2. Delta H is positive and delta S is positive. Positive, positive, that's going to give us the result where it is spontaneous at, it's going to be spontaneous at high temperatures. But let me go back. So positive, positive, it will be spontaneous at high temperatures. So I'll put spontaneous at high temperatures. Okay, so now we want to look at number 66. So here is number 66. Let me get it all there. Okay, well, looking at this, we'll see, let's see, it gives us our value for delta H and for delta S. So it gives us a value for delta H and for delta S. And with that, we can determine what kind of reaction it's going to be. So we want to calculate delta G for this reaction at 298. If it were at any other temperature, we can just use that formula. So we can calculate that at 298. Let's first of all figure out what kind of reaction this is. Is it spontaneous at low temperature, high temperature, no temperature, or all temperature? And with positive, positive, I'm going to go back here. You'll see with positive, positive, that's an example of a reaction that is spontaneous at high temperatures. So let's see if 298 is a high enough temperature for this reaction to be spontaneous in the forward direction. So let's see. Okay, so we'll do delta G is equal to delta H minus T delta S. Our delta H value was 572 kilojoules. Our temperature is 298 Kelvin. The delta S is 179 joules per Kelvin. And then we need to convert that into kilojoules. So 1 kilojoule over 1,000 joules. Make sure my calculator is visible on the camera. So we'll do 572 minus 298 times 179 divided by 1,000. And that gives us a value of 518.6. We're going to call that 519. So that equals positive 519 kilojoules. Well, I think everybody would agree with a delta G of positive 519 kilojoules, that reaction is not spontaneous in the forward direction. So we need to do the next part, which is at what temperature would it become spontaneous? Well, let's go back. If we want to know at what temperature it's going to become spontaneous, well, this is the example where we've got positive, positive. So I'm going to go back to the graph. So positive, positive. With positive, positive, it's the blue line. And we want to see at what temperature it crosses over this x-axis. Well, it will cross over that x-axis at the point where delta G is equal to 0. And when delta G is equal to 0, that's where it will be in equilibrium. So it crosses the x-axis where delta G is equal to 0. So we're going to go back. And when we go back, we are now going to say, well, delta G. Where delta G is equal to 0, we will get this. 0 is equal to delta H minus T delta S. And we want to solve for what temperature this is true. So we can move this T delta S over to the other side of the equation. So we'll get T delta S is equal to delta H. And now we can divide both sides by delta S. So temperature is equal to delta H over delta S. So we can put the values in here. Our value here is 572 kilojoules. So 572 kilojoules. And I do write the units. And the reason I like to write the units on problems like this is because if we don't write the units, we're going to forget that the entropy and the enthalpy are written in different units of energy. So 592 for the entropy, it's 179 joules per Kelvin. I'm going to write that down as 0.179 kilojoules per Kelvin. All right, and that makes our conversion pretty easy here. So we'll do 572 divided by 0.179. And that gives us 3196, so 3196 Kelvin. We need to round that to 3 sig figs. So if we round that to 3 sig figs, we're going to call that 3.20 times 10 to the third Kelvin. or about 3,200 Kelvin, which, in case you're wondering, that is quite toasty. That is quite toasty. So that is the answer to number 66. So we want to look at one more thing in this section before we go to the section talking about equilibrium constants. So here in this particular segment, we'll be talking about how free energy is related to work. And this kind of gives a meaning to what free energy is talking about. So what does this quantity even mean? And so we'll find that the change in free energy for a process equals the maximum useful work that can be done by the system on the surroundings in a spontaneous process occurring at constant temperature and pressure. So I just read that to you guys, so hopefully you're not too badly insulted by that. Sorry. But here's what this means. If you calculate delta G, that is going to tell you how much work you potentially could extract out of your system. It's the maximum amount of work. It's that theoretical maximum amount of work. You can't get any more than that. Now, the reason that that number is negative is because by convention, when work is being done by the system on the surroundings, then the value for W is going to end up being negative. So we do this little sign switch here, and hopefully that's not too terribly confusing, but this is our formula. So delta G will give us this. So let's look at number 69 on the in-class assignment. So let's read the problem. So acetylene gas is used in welding. I don't know if any of you guys are familiar with welding, but if you burn acetylene gas, it burns at a really, really high temperature. And the reason is that the delta H of this reaction is extremely high. First, we want to write a balanced equation for the combustion of acetylene gas to carbon dioxide and water, and we're going to point this out that that's water liquid. So that's right. C2H2 gas. When we burn it, we're going to be burning it in oxygen gas. And I'm going to put little spaces here for the coefficients that we're going to write here in just a moment. And so the products are going to be carbon dioxide gas plus, and it is specified here, H2O liquid. And on this one, it's asking us to calculate the heat. But before we do that, we need to balance this. So let's go ahead and balance it. Okay, well, the very first thing I like to do when I'm balancing it is to pick something that I'm going to work with. I'm going to work with carbon. Oxygen would be the worst thing to work with because it's in everything. I'm going to work with carbon. We've got 2 carbons here, 1 carbon there. I'm going to lock these 2 carbons in place by putting a 1 there and then put a 2 in front of carbon dioxide. So now carbon is balanced. Let's look at hydrogen next. We've got 2 hydrogens here, but over here we've got 2 hydrogens. So I'm going to lock those in place. So we've got hydrogen is balanced. Now let's count up the number of oxygens that are locked in place over here on the right side. 2 times 2 is 4. 1 times 1 is 1. So 4 plus 1 is 5. We need to get 5 oxygens out of this O2. And the way that we're going to do that is that we're going to use the coefficient of 5/2. Now, normally when we're balancing equations like this, we really like to have whole number coefficients. But because of the way this problem is worded, how much heat is produced in burning 1 mole, we're going to leave it like this because we want the heat of combustion per 1 mole of that acetylene. Now, it also is going to ask for the useful amount of work, so we're going to need to know delta G of formation as well. So we're going to go to the table and look up the delta H of formation for each of these and the delta G of formation for each of these. And before I look them up on the table, I already know one of them is going to be 0 for both of these on oxygen. And that's because oxygen is an element in its elemental form. Now, I'm going to spare you watching me go look up the values on the table. So using a little bit of magic, I'm going to make the values appear right here, right now. Ta-da! All right, so there we go. I wrote those out. That was the worst magic trick ever. Okay, so now that I have done that, we're going to calculate delta H for this reaction. So delta H, it's going to be products minus reactants. So delta H, so we'll have 2 times negative 393.5 plus 1, 285.83 minus 1, 226.77 plus 5 halves times 0. And we'll punch all that into our calculators. All right, so that is that side of the expression. Now we're going to subtract this. So minus and 5 halves times 0 is 0. So I'm just going to put that. And there we get negative 1299.6. So negative 1299.6 kilojoules. All right, well, that's definitely very exothermic. That's a lot of heat, which is the big reason why if you do this particular reaction, if you burn acetylene, it produces very, very high temperatures, and that's simply because it produces a lot of heat. Okay, so there we go. That is delta H. That is delta H. Now we want to calculate delta G, because the next problem is, what is the maximum amount of useful work that can be accomplished? Well, delta G is going to be equal to negative W max. So let's calculate delta G. Okay, so there we go. We've got that. Let's go ahead and punch these into our calculator. Let me just make sure I didn't enter the numbers in incorrectly. I think we're okay. That's parentheses. Okay, so okay, that is this part, and now we'll subtract 1 times 209, and that's 0, so just subtract 209, so 209.2, and that gives us negative 1235.13. And for sig fig purposes, tenths place, hundredths place, tenths place, we're going to round that to the tenths place. So we will round that to negative 1235.1 kilojoules. So that means since W max is equal to negative of our delta G, this is just a rearrangement of that. That means that's negative of negative 1235.1 kilojoules. Then our maximum amount of work is 1235.1 kilojoules. So what that means is if you had a very efficient engine and you put the acetylene in, So if you had a very efficient engine and you put the acetylene into there and you were able to convert all of the free energy into work, you potentially could do this much work. It's a maximum. In reality, we can never do that much work. In reality, there's no such thing as a perfectly efficient engine. So, so that is something that we want to avoid. All right. Well, I'm going to cut this video off, and we'll have one additional video after this that is going to be related to free energy and equilibrium. And there's several problems that we're doing on that one, so that's why I'm going to separate that into a separate video.